For decades, Java concurrency operated under a strict hardware constraint. Every thread required a rigid one-to-one mapping to an operating system kernel thread. That design enforces a massive physical penalty. Because the operating system manages these threads, the JVM must pre-allocate a fixed chunk of off-heap stack memory, typically a full megabyte, simply to track method execution frames for every single thread. This diagram illustrates the immediate scaling math of that one-to-one model. If you attempt to hold 10,000 concurrent network connections, your application instantly consumes 10 gigabytes of raw memory before executing a single line of business logic. Memory footprint is only the first bottleneck. The second penalty hits the CPU every time one of those threads encounters a blocking I/O operation, like waiting for a database query to return. When a thread blocks, the operating system kernel must actively intervene. It has to suspend the thread, flush the physical CPU registers, and swap in a different thread to keep the silicon busy. At enterprise scale, this constant cycle of context switching burns through CPU cycles. Scaling under this legacy architecture forces you into a corner where you will either run out of memory from thread stacks or starve your CPU through context switching overhead. We can see exactly how this limitation causes production failures by examining a sudden traffic spike of 5,000 concurrent tasks hitting a legacy microservice. A standard defense mechanism for this scenario is a bounded thread pool. Consider a common configuration: 5 core threads to handle the baseline, a maximum of 10 for bursts, and an unbounded work queue to hold overflow. As the traffic hits, the thread pool executor spins up its 5 core worker nodes. The first 5 tasks route cleanly into active memory and begin processing. The fatal flaw lies in the queue sitting below those active workers. Because it was initialized without an explicit size limit, its default capacity evaluates to integer.maxValue. It is functionally infinite. The executor never spawns the 6th or 10th thread. Since the queue expands forever, the condition triggering the maximum limit is never met. The remaining 4,995 tasks dump endlessly into the queue, inflating the heap until the application crashes with a fatal out-of-memory error. Putting hard limits on queues prevents the crash, but it means dropping requests. To actually process tens of thousands of concurrent tasks, we have to abandon the OS thread pool entirely. Project Loom, introduced in Java 21, bypasses the operating system entirely. It moves thread scheduling out of the OS kernel and executes it directly inside the JVM user space. The heavyweight platform thread is replaced by the virtual thread, a lightweight execution unit that requires almost zero memory overhead to instantiate. To process these units, the JVM spins up an internal ForkJoinPool. This pool maintains a small, fixed number of platform threads, known as carrier threads, matching the exact number of physical CPU cores on the machine. This creates an M-to-N execution model. You can instantiate millions of virtual threads, hovering in user space, while they share a highly restricted pool of physical carrier threads underneath. When a virtual thread is ready to execute its business logic, the JVM's internal scheduler mounts it directly onto an active carrier thread, connecting it to the hardware. By handling the mapping in user space, the JVM completely insulates your application code from the native limits of the operating system memory and CPU swapping. The true efficiency of this architecture reveals itself the exact moment a virtual thread hits a blocking system call, like requesting data from a downstream REST API. Instead of letting that blocking instruction reach the OS kernel, which would stall the physical CPU, the underlying Java core library intercepts the call. At the moment of interception, the JVM utilizes an internal memory abstraction known as a continuation. As you see here, the virtual thread's execution state, instruction pointers, and local variables are cleanly packaged into this continuation block and moved completely off the execution track, down onto the standard Java heap.
This is the unmounting process. The virtual thread physically detaches from the carrier thread. The carrier thread never waits for the network response. It is immediately freed, and the JVM instantly mounts a completely separate virtual thread onto it. The physical silicon never stops calculating. Once the operating system signals that the network I/O has completed, the JVM alerts the continuation. The stack frames are copied from the heap back onto a free carrier, and the original virtual thread seamlessly resumes execution right where it left off. Moving the wait state to the Java Heap means you can maintain thousands of concurrent database connections without wasting a single CPU cycle or triggering a native kernel context switch. It is highly dangerous to treat virtual threads as flawless drop-in replacements for platform threads in legacy codebases. If you migrate an older microservice to Java 21 without refactoring, you will trigger a severe operational failure mode known as thread pinning. Pinning occurs when a virtual thread enters a specific state where the JVM's unmounting engine is blocked. The continuation cannot safely package its stack frames, and it cannot move to the heap. This code comparison shows the primary trigger. Executing a blocking network call inside a legacy synchronized method or block wraps the execution inside a native object monitor lock. Current JVM architecture cannot unmount a continuation from inside a native monitor. When that blocking network call fires, the virtual thread cannot detach. It acts as an anchor. The underlying platform carrier thread is forced into a hard stall, waiting for the I/O to finish alongside the virtual thread. To prevent your carrier pool from starving, you must systematically refactor legacy synchronized wrappers into explicit re-entrant lock structures. Re-entrant locks natively support the Loom unmounting engine. Upgrading a cluster to Java 21 without auditing your synchronization paths will paralyze your hardware and turn a platform upgrade into a production outage. Running this architecture securely requires abandoning concurrency habits that have governed Java development for over 20 years. The legacy mandate was to always pool threads to defend against memory limits. The modern Loom rule is the exact opposite: never pool virtual threads. Because virtual threads consume practically zero memory overhead when sitting idle, the entire concept of thread lifecycle reuse is completely redundant. This breaks traditional rate-limiting strategies. If you attempt to throttle downstream traffic to an external database by limiting your thread count, the strategy will fail. Virtual threads are unbounded. You can spawn 1 million of them in seconds. To enforce actual concurrency limits in a modern microservice, you must use explicit semaphore partitions to govern the maximum number of simultaneous outbound requests. You instantiate a virtual thread exactly when you need it, and you let the JVM discard it the millisecond the task completes. When a virtual thread implementation bottlenecks in a production environment, traditional debugging tools will fail you. Extracting a legacy thread dump via JStack is useless. It cannot catalog millions of threads and will freeze your pipeline. Instead, execute the modernized system command jcommand thread.dump_to_file. This command specifically categorizes your active carrier execution lines and separates them from your unmounted, heap-parked virtual threads. To detect pinning conditions in real time, you must run your containers with JVM Flight Recorder enabled. You audit the flight recorder tracks for the specific diagnostic token jdk.virtualThreadPinned. This event captures the exact millisecond a carrier stalled and points directly to the source code location of the native monitor lock causing the failure. Implementing Project Loom is an architectural reset. It requires you to stop managing thread life cycles, understand memory unmounting, and wield advanced runtime diagnostics to keep your carrier threads moving.